students, here is Mr. Ramesh Chandra and taking lecture on complex numbers. I am taking this lecture by considering HSC board, CBSE board and IIT JEE main and advanced preparation. So let's start with the history part of the complex number. Number system hierarchy. These are the various number that we know till now. N for natural number, W for whole numbers, I for integers, Q for rationals, QC for irrationals, R for real number, and C for complex numbers. So let's talk about the natural numbers. Natural numbers. So these are the number used in counting, like 1, 2, 3, 4, 5 and so on up to infinity. Whole numbers, a number 0 is included in the natural numbers. So whole numbers start with 0, 0, 1, 2, 3, 4 and so on up to infinity. And then we have integers, 0, plus minus 1, plus minus 2, plus minus 3 and so on. And then we came up with rational number defined by Q, rational number in the form of P upon Q, where P and Q both are integers and Q not equal to 0 are rational numbers. Even HCF of mod P mod Q should be equal to 1. So number like 1, 2, 1 by 5, 7 by 6, 9 by 7. These are some rational numbers. Then we come up with irrational numbers like QC. QC is the symbol to denote irrational numbers like root 2, pi, e to the power pi, etc. 1 plus root 3, like this. These are the irrational numbers, set of irrational number. Now if we take rational and irrational number union irrational number, then we will get a set of real numbers. So real numbers are all these numbers are said to be real numbers. And then we come up with the idea of imaginary number I, and then we define a complex number C. C is for complex numbers. And as you can see here, the natural number is a subset of whole numbers, and whole number is a subset of integers, and integers is a subset of rational numbers. If we combine rational and irrational both, then we will get real number set, and real number is a subset of complex numbers. So complex number or complex field is the largest field that we know today. So we can have a relation like natural number is a subset of whole number, and whole number is a subset of integers, and integer is a subset of rational number. We can't have irrational number at here. So in the same way, rational number is a subset of real numbers, and real number is a subset of complex numbers. So this is the hierarchy of number system. Let's talk about the need of the complex numbers. Here is the fundamental theorem of algebra. As per the fundamental theorem of algebra, we have a statement: n degree polynomial equation has exactly n roots. What does it mean? N degree polynomial equation has exactly n roots. Let's understand by some example. We have a simple linear equation as 2x minus 3 equal to 0. This is a linear equation and hence its degree is 1, so it must have one root. So as we can have, x is equal to 3 by 2. This is a root of this equation. Similarly, let's say we have equation like x minus 1 into x minus 2 is equal to 0, that is x square minus 3x plus 2 equal to 0. So this is the quadratic equation having two roots, 1 and 2. As if you put 1 in this case, this will satisfy, or 1 minus 1 into 1 minus 2 is equal to 0. So you can have 1 minus 1 is 0. So 0 into 1 minus 2 is minus 1, that is equal to 0. So this is true. So 1 and 2 are satisfying this equation. Hence 1 and 2 are root of this equation. Now let's come up with the equation like x square plus 1 equal to 0. Since this is a quadratic equation, so it must have two roots. Now if we think of a natural number like 1, then 1 square plus 1, that is equal to 2 and not equal to 0. So x is equal to 1 is not a root, root of this equation. Now let's check x equal to minus 1, whether it is a root or not. So if we put x equal to minus 1 in this equation, call this equation number 1. In the equation 1, then minus 1 square plus 1, that is equal to 1 plus 1, that is 2, and still not equal to 0. Now can we think another number? You can see the natural number, rational number, irrational number, and every real number can't explain the root of this equation. So there must be some kind of number system that explain the roots of this equation, like x square plus 1 equal to 0. Hence we invented complex number and define x square as minus 1, and then x is equal to under root minus 1, and define this to be iota. We define under root minus 1 as iota. So if we solve this equation, then we will get two roots for this quadratic equation, plus minus under root minus 1. And we define under root minus 1 as iota. So you can see here, now this equation can be written as x square minus 1 under root whole square is equal to 0. So we will have two roots for this, as x square is equal to under root minus 1 whole square. This implies x equal to plus minus under root minus 1, or x is equal to plus minus iota. The equation x square plus 1 equal to 0 has two roots. One is iota and another is minus iota. Let's talk about iota. As x square plus 1 is equal to 0 has root iota and minus iota. So iota will satisfy this. You can see here. Iota is equal to under root minus 1. So iota square must be equal to minus 1. If we square this, you will get minus 1 here. Now if we multiply both sides by I, then you will get I square into I is equal to minus 1 into I, and that is equal to, that's imply I to the power 3 is equal to minus I. Minus 1 into I is minus I, and since base are same, so power will add up to 3. So I cube is equal to minus I. Now if we again multiply by I in this equation, then we will get I to the power 3 into I is equal to minus I into I, and that imply I to the power 4 is equal to minus I square. And we know that I square is minus 1. So this is minus of minus 1, that is equal to 1. So I to the power 4 is equal to 1. So let's generate some series here. That is I is equal to I square is equal to minus 1, and I to the power 3 is equal to minus I, and we get I to the power 4 as 1. Now if we again multiply by I in this equation, that is I to the power 4 is equal to 1. If we multiply again by I both sides, then we will get I to the power 5 is equal to I. So this implies I to the power 5 is equal to I. Now if we again multiply by I, then we will get I to the power 6 is equal to I square, and I square is equal to minus 1. So we put here minus 1. So I to the power 6 is equal to minus 1. So I to the power 6 is equal to minus 1. That's right here. Now again multiply by I, we will get I to the power 7 as minus 1 into I, that is minus I. So write it here, I to the power 7 as minus I. On multiplying again by I, then I to the power 8 is equal to minus I into I, that is minus I square, and I square is equal to minus 1. So we will have minus of minus 1, that is 1. So I to the power 8 is equal to 1. Similarly, again we multiply by I, then we will get again I to the power 10 is equal to I square, and I square is equal to minus 1. So what we are getting here, I to the power 9 is equal to I, and I to the power 10 is equal to minus 1. I to the power 11 must be equal to minus I to the power 12 is equal to, that is 1, and so on. So you may be observing some pattern that I to the power 1 is equal to I to the power 5 is equal to I to the power 9, and so on. You can observe that we are getting the same pattern again and again in multiplicity of 4. I minus 1 minus I 1, I minus 1 minus I 1, and so on. So you can see there is a gap of 4. 1 plus 4 is 5, 5 plus 4 is 9, and then we will have I to the power 9 plus 4, 13, and I to the power 13 plus 4, 17, and so on. So these are all equal to iota. So you can observe I to the power 1 is equal to I to the power 5 is equal to I to the power 9 is equal to I to the power 13 is equal to, and so on, and this is equal to I. And you can observe here that 1, 5, 9, 4 are the numbers 1, 5, 9, 13 are the number which are of format 4n plus 1. What does it mean by 4n plus 1? If we divide these number by 4, then we will get remainder as 1. If we divide 5 by 4, then you will get remainder 1. If we divide 9 by 4, then you will get remainder as 1. So in general, we can have I to the power 4n plus 1 is equal to I. Now let's talk about these numbers. What are you observing here? I square is equal to I to the power 6 is equal to I to the power 10. As you can see, is equal to I to the power 14 is equal to, and so on, and this is equal to minus 1. 2, 6, 10. Let's observe these numbers 2, 6, 10, 14, and so on. These are the number of type 4n plus 2. These are the number of types 4n plus 2. If we divide these number by 4, you will get remainder 2. So in general, we can have I to the power 4n plus 2 is equal to minus 1. Now let's observe again IQ that is equal to I to the power 7. 7 is equal to I to the power 11 is equal to I to the power 15 is equal to I to the power 19 and so on. And these are equal to minus I. So these are the number. So these are the number of type 4n plus 3. So I to the power 4n plus 3 is equal to minus I. In the same way, if you think of I to the power 4 equal to 1, I to the power 4 is equal to 1, and this is equal to I to the power 8 is equal to I to the power 12 is equal to I to the power 16 and so on. And 4, 8, 12, 16 are of the type 4n. 4, 8, 12, 16 are of the type 4n. If we divide these number by 4, then this must be divisible by 4. So this implies I to the power 4n is equal to 1. So in general, let's have a general case. I to the power 4n plus 1 is equal to I, and I to the power 4n plus 2 is equal to minus 1. I to the power 4n plus 3 equal to minus I, and I to the power 4n is equal to 1. What does this mean? Let's have some cases like I to the power 200. Now 200 is of the form 4n. So 200 is divisible by 4, then this is equal to 1. Now let's talk about I to the power 70123. Now you can observe here 70123 can be written as 70100 plus 23. So if we divide only 23 by 4, then we will get remainder 3, you can see. So 70123 is of the form 4n plus 3. So as you can see here, 4n plus 3, hence this must be equal to minus iota. Now let's talk about I to the power 2017, and you can observe that 2000 is divisible by 4. So we need to divide only 17 by 4. Then if you divide 17 by 4, you will get remainder 1. So 17 is of the form 4n plus 1. Hence this is equal to I to the power 4n plus 1 is equal to iota. Now let's talk about I to the power 1371. Let's say. Now we need to think of only 71 for 71. 71 is of the form, we divide by 4, you will get remainder 3, 31. This is of the form 4n plus 3. So this is equal to minus iota. Now let's talk about the complex number, and it is the definition of complex number. We define any complex number z as a plus iota b, where a and b are real number and iota is defined as under root minus 1, like 2 plus iota 3. You can observe here 2 and 3 both are real number. 2 and 3 both belongs to real number. So this is a complex number z. We can define it by z. Now let's say we have a number z1 as minus 2 plus under root minus 3. So what does it mean? We can write it as minus 2 plus under root minus 1 into under root 3. So this is minus 2 plus, since this is equal to iota root 3. We can write minus 2 plus under root minus 3 as minus 2 plus iota root 3. Like we have a number z2 as 3 times under root minus 16. So we can write it as 3 times under root minus 1 into under root 16, and under root 16 is 4. So 3 into 4, and under root minus 1 is iota. So this is 12 iota. Hence this is equal to 12 iota. Let's say we have Z3 as 5. Now 5 is a real number. We can write it as, always we can write it as 5 plus 0 iota. So B is equal to 0 in this case. Now let's talk about Z4 is equal to 7 plus under root minus 1 plus 2 under root minus 1 minus 7 under root minus 1. So what we can have for this as we can have 7 and under root minus 1 is iota, so plus iota, and this plus 2 iota and minus 7 iota. So you can observe here, this is 7 and 1 iota, 2 iota, and this is minus 7 iota, so this is minus 4 iota. So you can see we have expressed any number in the form of a plus iota b. In this case, a is equal to 7 and b is equal to minus 4, and both are belongs to real. So any number of the form a plus iota b is said to be a complex number in which a and b are real numbers. Let's talk about three different kind of complex number. Let's Z1 is equal to 2 and Z2 is equal to 5 iota and Z3 is equal to 7 plus 4 iota. You can see here. What are you observing in this case? You can observe here there is no IB part in this case. So even you can say this as a real number. So every real number is a complex number, you can see. Even we can write this as 2 plus iota 0. So in this case you can see B, that is associated with I, is 0. B is equal to 0, and this kind of complex number is called purely real. Z1 is purely real number. You can observe here there is 5 iota and b is equal to 5 in this case, b equal to 5, and a is equal to 0. We can write it as 0 plus 5 iota. So this kind of number is known as Z2 is purely imaginary number, and in this case we can say this a imaginary number. This is purely imaginary number and this is imaginary number. Why it is so? Since in this case b is not equal to 0, b is not equal to 0 and this is equal to 4. b is 4, which is not equal to 0. So if any number of the form a plus iota b in which b not equal to 0 is called imaginary number. And there is a difference between purely imaginary and imaginary number. You can observe here. We can also say 5i as imaginary number, but we cannot say 7 plus 4i as purely imaginary number. Now in this case, a is called real part of z, and in short notation we can define as REZ. So REZ is equal to a, and b is known as, b is called imaginary part of z, and denoted as I am z. That is a short notation. So imaginary part of z is b. Like z1 is equal to 7 minus 2 iota. So real part of z1 is equal to 7 and imaginary part of z1 is minus 2. The number associated with I is the imaginary part when it is in the form of a plus iota b. Like z2 is equal to 7 minus 7 plus 4 iota. Then real part of z2 is equal to minus 7 and imaginary part of z2 is equal to 4. So A is called real part of Z and B is called imaginary part of Z. Let's have a better understanding of complex number A plus iota B. And here we have taken three situations: B equal to 0, A equal to 0 and B not equal to 0. This is the case. If B is equal to 0, then you will say that imaginary part of Z is 0. If this is 0, then Z become Z has only real part and no imaginary part. Now in this case, you can observe if A is 0, then Z have only imaginary part, and in this case you can say real part of Z is equal to 0. A is real part of Z, so real part of Z is 0. And in third case, you can observe here, B is not equal to 0. A may be 0, A may not be 0. So both situation is included here. So we have three cases. So if we say imaginary part is 0, this implies Z is purely real. So either we can write it by this, or I can write this, or we can say Z is purely real. If there is a question like Z is purely real number, so then we can assume any Z as K, where we define K to be real. If it is given in the question that Z is purely real, then we can assume Z as K. K belongs to real. Now let's talk about second case. If A is 0, that is real part of Z is 0, this implies Z is purely imaginary. Z is purely imaginary. Now if there is a question in which it is given that Z is purely imaginary, then we can assume a complex number Z as K iota, where K belongs to real number. Since it is given in the question, hence at that time we assume Z as K iota. And if B is not equal to 0, A may say 0, A may not be 0, then in that case imaginary part is non-zero. Hence in this case we call Z is a imaginary number. And in this case we cannot write Z as Ki or Z is K. If there is a question on imaginary number, then we have to assume Z as A plus iota V or Z is equal to X plus iota Y. We have to assume to solve the questions. And you can observe Z is equal to 0 is both purely real as well as purely imaginary number. You can see Z is equal to 0 can be written as 0 plus 0 iota. So it is satisfying both the condition, this as well as this. Hence we call Z is equal to 0 is purely real as well as purely imaginary number. And this is the only complex number which is both imaginary as well as real.